Hi, this is Mrs. LaBarbara. Today I'm talking about significant figures or significant digits. The objective of today is to know the meaning of significant figures, to know the rules of determining significant figures from a given measurement, and the difference between accuracy and precision, to be able to determine significant figures in calculations. Significant figures represent the level of certainty in a measurement. So in a measured value, the digits that are known with certainty plus the one digit whose values has been the value of certainty is 5.3. After that, you'll have to estimate what is the next value. So I estimated to be 0.01 centimeters. So in this measurement, I measured the length of the strip would be 5.31 centimeters. So in all these three digits are significant. The number of significant figures depend on how precise an instrument is. So suppose you are trying to use this ruler to measure the thickness of your hair. That would be it's not a good instrument to measure the thickness of hair. So you wouldn't have many significant figures. You probably just have one. Let's take a look at another example. How long is the block? You're using a ruler to measure the length of the block. So the digit for sure you know is 1.3. Now over here, you can estimate. I estimated to be 0.6. So it would be 1.36 centimeters. So again, in this number, all three figures are significant. Here is an example to measure the mass. This is a picture of a triple beam balance. So to read this, you read the first largest scale first, then you read the second largest scale, then finally the least scale. So the first one give you 0, the second one is 60, so 62 grams. Then you'll have 4, so 62.4. Then you estimate over here. I estimated to be 0. So the total mass is 62.40. In this number, 62.4 is for certain. This 0 is estimated. So total significant figure in this measurement is 4. Now, what are the rules to determine significant figures in a measurement? So if a digit is a non-zero, it is significant. For example, 43.74, all digits are non-zero, so everything is significant. So there are 4 sigfigs. Now, if it is 0, there are 3 scenarios. 0 can be between non-zero digits. 0 can be the leading zeros or can be ending zeros. Now, if 0 is between non-zero, then they are significant. The leading zeros are not significant. For example, 0.892. This 0 is a leading 0. It's not significant. So in this number, you will have 3 sigfigs. Now, in this number, the next one, all the zeros are leading zeros. So this number has only 1 sigfix. This 0, it's between the non-zeros. So they are significant. So the total have 5 sigfigs. This number, 0.305, the first 0 is a leading 0, not significant. The second 0 is significant because it's between non-zero. So this has 3 sigfigs. Now for ending zeros, there are 2 rules. If there is a decimal point, then zeros are significant. 30.00. Decimal point, all the ending zeros are significant. So this number has 4 sigfigs. This number, leading zeros are not significant. Ending zeros is significant because there is a decimal point. So this number has 2 sigfigs. If there is no decimal point at the end, then zeros are not significant. That means ending zeros are not significant. This no decimal point, ending zeros are not significant, so this number has only one sig fig. 20 millimeters has no decimal, ending zeros is not significant, so it only has one sig fig. Some practice. First number, ending zeros, no decimal, not significant, 3. Leading zeros are not significant, so you have only 2. Ending zeros, you have a decimal, significant, 4. 0 in between non-zero, significant, 5. First, non-significant, second, significant, so total is 3. Expressing significant figures using scientific notation. So sometimes scientific notation is necessary to express significant figures. For example, in this number 2000, it has 1 significant figure. If I want to express with 4 significant figures, I can put a decimal, right? However, how to express 2000 with 2 significant figures? That is very hard. How do you do it? One way to do it is to use scientific notation. So we can use 2.0 times 10 to the 3 meters. In this number, it has 2 significant figures. So that's represent in this, the whole number 2000, there are 2 significant figures. Similarly, to express 2000 with 3 sig figs, you simply use the first part. First express that as 3 sig figs. We can determine significant figures when we multiply or divide. What's the rule? When you multiply or divide, the answer has the same number of significant figures as the measurement having the smallest number of significant figures. What does that mean? Let's look at an example. What is the area of the rectangle that has 9.8 centimeters by 12.7 centimeters? Now we should know, or you should know, the area is the length times width. So it doesn't matter which one is which. So these 2 numbers multiply together. The first number has only 2 sig figs. The second number has 3 sig figs. So your result should have the smallest number of significant figures, which is 2. So the answer, after you multiply these 2 together, you should have 120 centimeters squared, because the result should have only 2 sig figs. Now, accuracy and precision can be interchangeable in everyday conversation. However, in physics, they mean different things. Accuracy is a measurement that is the degree of closeness to the measurements of that quantity's true value. So how close to its real value. Now, precision of a measurement is the degree to which repeated measurements under unchanged conditions shows the same results. So you measure the table 3 times, for instance, and all 3 times you have a very, very similar value. Then your measurement is precise. So to be accurate, your measured table has to be very close to the true length of the table. Then your measurement is accurate. For example, Matt measures total length of the lap around the school's track to be 402.3 meters, 402.3 meters, and 402.5 meters. If accepted value for the path length is 402.3 meters, are Matt's measurements accurate? Explain your answer. So the measurement of 402.3, 402.3, 402.5, they are all very close to the true value. How do you know it's very close? Because it's only the last digit changes a little bit. So that is very accurate. Now, is his measurement precise? Precise is his measurement close to each other in this case. They are close to each other also because the only difference is the last digit. So the answer is precise because they are very close to each other. Another example. Mike measures the speed of red light in ice to be 2 times 10 to the 8th, 1.87 times 10 to the 8th, and 2.39 times 10 to the 8th. If the accepted value of the speed is 2.25 times 10 to the 8th, are Mike's measurement accurate? Explain. Now, his measurements are not accurate because it's not only last digits change. The one before the last also change. So that's why they are not accurate. They are not close to the true value. Are they precise? No, they are not precise. Even those 3 numbers, they are a big difference because they are, in order to be precise, should be only the last one change. So as you can see, that's not true. So I hope it helps. See you next time.